Hey guys, Professor Floyd here. We're going over homework 8 of OEH 5723, and this is problem number 1. So I've asked you to compare and contrast the strengths and weaknesses of a PID, an FID, or an NDIR detector. And so, and then I also asked you to decide which of these instruments you might use to leak detect a methane leak in, say, a residence, somebody's, or maybe a commercial industrial setting where somebody's reporting the smell of natural gas and they've confirmed they have an HVAC system that's not working correctly. And so maybe their furnace is not fully igniting, who knows. So you're going in there to see, what is this thing? Is it a chemical that's being released, or is it indeed the natural gas? And it's that dopant in natural gas that you smell really strongly. So first off, FID, of course, is flame ionization detector. This is a hydrogen flame combustion, so it's hydrogen plus oxygen, so that makes water. It doesn't go through any positive ion intermediates, but it will burn any hydrocarbons that come through it, and as those hydrocarbons come through the detector or come through the flame, they make positive ion intermediates, and those positive ions are drawn to an electrode which gives a signal, and that signal is an electric current because it's starting to ground the voltage difference between two plates. And so it takes electricity, it takes current to keep that voltage difference constant. So that's generally how an FID works. So FIDs are very good because they're responsive to a broad chemical class. They have greater response to ethane than methane. So the more carbons there are in the base molecule, the greater the response. So if you had 1 mole of methane run through an FID, you might get a response of 1, and if you had 2 moles of benzene or hexane run through that same FID, you wouldn't necessarily get 6 times the response, but you would get a larger response because there's 6 carbons in hexane and there's only 1 carbon in methane. So an FID is got a very good linear dynamic range. So 1 ppm is detected just as good as 10,000 ppm. And so oftentimes it's got about 5 orders of magnitude. So it might go from 0.1 ppm to 10,000 ppm and stay linear. So that's good, but it uses a flame, so it's not going to be very suitable for a potentially explosive environment. It also has loss of sensitivity the more substituted the molecule is that you're monitoring. The less it will respond to an FID, the more blind the FID will be. So if you have oxygens, if you have rings, if you have double bonds, you'll have a lower signal response from your FID. That is why carbon disulfide was the solvent of choice when industrial hygiene methods were being developed in the 70s and 80s, because flame ionization detector was the primary detector on gas chromatographs. So the GC was feeding the chemicals that it was separating into an FID, and you were getting a signal. Well, if you extracted in carbon disulfide, the sulfurs are analogous to oxygens, and it had a fairly neutral response at the PID, at the FID, the flame ionization detector. So it was considered to be transparent. It's not really, but compared to if you had extracted in hexane or some other organic solvent, you get a much lower solvent peak due to the carbon disulfide. And that's because of the way the FID behaves. So they definitely have their benefits, but they have some limitations that I just discussed. The photoionization detector, the PID, has recently become very miniaturized, and it's actually, I've got one here on my desk. I didn't think about this. I didn't actually set this up, but this is the size of a PID in most handheld 4 gas meters. This one is manufactured by Baseline Mocon. you can see this thing is small. And so the sensing cell is just below that white spot, and the whole thing is small. It has 3 electrodes, ground, and then signal and supply power. So these devices run off of generally about 5 volts, but they run off of low voltage battery powered devices. They don't require a lot of energy. They have a little UV lamp inside underneath an electrode stack. That UV lamp shines high energy photons. Those high energy photons can knock off electrons from electron dense molecules and ionize them. It causes them to lose a negative charge, lose an electron. So you have positive ions that get formed from that UV lamp, that low short wavelength high energy photon. And that positive ion is drawn to a negative electrode. The same thing like with the FID. The amount of electricity or flow of electrons it takes to maintain that difference in voltage between the electrode stack plates is a current, and that's proportional to the concentration of the analyte being detected, or the molecule being ionized. So it tends to be a non-discriminating ionization process. It's not a very efficient ionization process, but it's quite sensitive. It has a very good linear dynamic range that rivals that of the flame ionization detector. Historically, it hasn't been as good. It's more like 4 to 5 orders of magnitude of linearity, whereas the FID is like 5 to 6. But I think recently it's gotten a lot better, and there's pretty much no difference between the two now. It will give the same response regardless of the number of carbons in the molecule. Or I shouldn't say it like that. I should say the number of carbons in the molecule doesn't directly affect the signal that you get at the PID, but the ionizability, or the number of electrons that can be liberated in that molecule based off their ionization potential, the first ionization potential, the second ionization potential, that can be different for molecules that might have a lot of electron density, like an aromatic ring has a lot of pi bonded electrons that are being shared, and if one gets kicked out, it's pretty easy, and maybe you can kind of get a second one periodically. And so it's got a higher response factor if you are an aromatic compound, or if you have a lot of pi bonds, some double bond electrons. And so the PID does not give the same response for every single chemical. Every chemical gives a slightly unique response. PIDs are usually calibrated with isobutylene, and then all other chemicals have response factors relative to isobutylene. So toluene, for example, will create roughly twice the amount of ions as isobutylene will. So if you have 1 ppm of toluene and 1 ppm of isobutylene, toluene will make 2 units of signal, and isobutylene will just make 1 unit of signal, roughly. And each PID is a little bit different, the way it's configured and tuned and everything. But generally, the response factor for toluene is 0.53. And then the response factor for benzene is very similar to toluene, because they both have that same benzene aromatic ring. And xylene, and so anyways, PIDs are quite useful because they do not combust, they're non-destructive, whereas an FID is destructive. PIDs do not make open flames, and they run off of battery-powered devices, and they can be intrinsically safe, is what I'm trying to say. So PID is useful for a lot of situations, but it's not unique, it's not specific to a compound. You can lower the ionization potential of the lamp. You can lower the energy of the lamp, and you can screen out molecules that have higher ionization potentials. Let's see here. And then an NDIR, non-dispersive infrared detector, is usually Basically you shine infrared light down a reference path that's sealed from the environment and down a path that is exposed to the environment, and the same infrared beam is being split and bounced back and forth between the reference path and the environmental path, and then it's being alternately routed to the detector, and so the detector knows the signal that's coming from the reference path and the signal that's coming from the environmental path, and it can calculate what the concentration is based off of difference in absorption. So that's nice. It doesn't usually need calibration very often, whereas an FID and a PID should be calibrated periodically, and they should have a bump test where you just expose them to a small quantity of VOC and make sure that the sensor is responding. That should be done on a daily basis with PIDs and FIDs. So NDIR is quite stable, solid state device, low energy usage. They typically, because they're infrared based, you're looking for a specific infrared absorption band. And so you're going to have to choose an infrared emitter that is emitting wavelengths at the same energy as a bond resonance or a bond shear or wag or stretch in one of the molecules that you're interested in. So you might choose a carbon-hydrogen stretch, in which case you'll be non-discriminant and you'll pick up pretty much all hydrocarbons. But you won't pick up CO2 because that'll be a very different energy stretch for that carbon-oxygen double bond. You might want to tune the infrared for an oxygen-hydrogen so you can pick up alcohols. But you know, you're only going to pick up alcohols. So NDIR is neat in that it's fairly low cost, it's got a lot of stability, it's low energy consumption, but it tends to be sort of molecule specific. It's chemical class specific or functional group specific is the better way to say it. And it has its limitations, a little bit greater limitation in that it's pseudo-selective, but not selective enough that you can really identify what that chemical is. So NDIR is also suitable for really high concentration measurements. So if you were tasked to find a methane leak, you could use an NDIR that might be set up for methane, for carbon-hydrogen stretch, and you could detect that way. Maybe it's set up as a lower explosive limit sensor. You could also use the PID. No, you couldn't use the PID because the PID is generally got an ionization potential of 10.6. High energy is maybe 11.2, but the ionization potential of methane is like 13.4. I've got it written down somewhere here. Sorry, it's 12.6. So you will not ionize methane with a PID, so you'll never see it. And that's one of the disadvantages to a PID. An FID would definitely pick up methane, but you know, what if you've got a high concentration of methane in a small little environment? You stick that FID probe down in there, you pull that explosive environment into your detector, perhaps you have a little explosion into your detector, perhaps you ignite that larger microenvironment and you have a little flash and cause an upset condition. Maybe you trigger limit switches within the systems. Who knows? So running into an area that could have high concentrations with an FID is not so smart. So I would choose an NDIR that's been tuned for the analyte of interest, and maybe have an FID as a backup. PID is not going to be a good choice in this case. So I hope that helps. That was kind of long-winded, but there was a lot of information that could have been covered based off of that.